You are all aware that this is one of the upcoming topics, particularly for the last I would say the origin is basically I would say from a paper in 1981 by a person by name Herbert Gleiter. Okay. So, Gleiter is from Germany, can be considered as a pioneer in the nanomaterials, and they have made nanomaterials of various metals and ceramics starting from 1981. The initial work was on pure metals by a technique called inert gas condensation technique. We will know more about it as we go to various techniques that are available for production of nanomaterials. So, basically inert gas condensation, as the name suggests, is basically a gas condensation technique. You make the metal in the form of a vapor and condense the vapor onto some kind of a cold substrate, and while condensation these vapors come together and form the nanocrystals, or you can call them as clusters depending on their sizes, and you get these things deposited onto a cold substrate, which is usually referred to as cold finger in a inert gas condensation technique, and you basically scrape these nano powders from the cold finger and then collect them and do whatever you would like to do. If you want to use them as nano powders itself, you can use them as nano powders, or compact them to whatever shape you want to have it, and then use them as a bulk material. So, this was the technique which has come up primarily due to the work of Gleiter in 1981, and then it has picked up a lot of momentum, and a number of people all over the world, including India, people have been working on this. Basically, if you look at nanomaterials, we have been talking about microstructure property correlations in the last class. So, particularly the basic difference between a nanomaterial and a micromaterial or a bulk material is basically that the grain sizes are much smaller than what we usually encounter in a typical material. For example, if we are talking of a steel, okay, a steel usually when we talk about the microstructure, the ferrite grain size, they are of the order of around 100 microns or so, and we do some special treatments for these steels to make them finer. For example, you are aware of high strength low alloy steels, HSLA. In HSLA, we try to refine the grain size by putting some pinning agents at the grain boundaries, for example, some carbides and nitrides, which can prevent the grain growth during the grain growth stage after the recrystallization. When you take the steel, heat it to high temperature, we know that whenever you heat a cold work material, there are 3 stages that are involved: the recovery, recrystallization and grain growth, and that grain growth stage, which is the 3rd stage, can be controlled by putting some hard particles at the grain boundaries, which act as pinning agents for the grain boundary to move. Okay. So, if you can somehow prevent the grain boundaries to move, you can control the grain size. This was the technique adopted in high strength low alloy steels. There are also many other techniques which are available to reduce the grain sizes. For example, one technique is deformation itself. Okay. When we deform a material, cold work a material, we know the grains get elongated and the sizes decrease. Okay, and then followed by a proper heat treatment to control the grain size, if you can stop it at the recrystallization stage itself, so that you can get a fine grain material. And during the production of the material itself, the most important technique that we use to produce materials in metallurgy is basically melting and casting, isn't it? So, in the melting and casting technique itself, there are a number of techniques available to control the grain size, which is, for example, what is called a vibration. You must have heard of techniques where the whole mold is vibrated, okay, thick casting, Rio casting techniques, where you break the dendrites which are growing in the liquid into the form of small fragments, and these fragments, when they finally meet each other, you get each one of those fragments becomes one grain and you get a fine grain structure. That is one of the technique. And the other technique we all know is the cooling rate itself. During solidification, if we can have a high cooling rate, we know that the cooling rate has a direct correlation to the undercooling that we can achieve, and if you have high undercooling ultimately that you know that the cooling rate, if we increase, the undercooling increases, and if the undercooling increases, we clearly know that the activation barrier for nucleation decreases and the critical size of the nucleus also decreases. We know these relations from our metallurgical principles, that R star is nothing but minus 2 gamma by delta GV. In our thermodynamics class we have learned this, okay, and in the kinetics class also you come across this. So, and delta GV is directly proportional to delta T. We all know that delta GV is nothing but delta HF into delta T by TF, isn't it? So, from that we know that delta GV is directly correlated to the delta T, and R star is obviously inversely related to the delta T. So, as a result, if you can have high cooling rate, we can have high undercooling, and that reduces the R star, and at the same time the delta G star, which is nothing but 16 pi by 3 gamma cube by delta GV square. This also you are all aware of. Okay. So, here also you can see the delta GV term is coming in the denominator in the square term, and because it is coming the square term, obviously there will be a delta T square term coming into picture. So, as a result, delta G star is inversely related to the square of the delta T. So, both R star and delta G star are inversely related to delta T, and we know that delta G star is the one which decides the nucleation rate. So, if you take the nucleation rate I, nucleation rate is nothing but some pre-exponential term multiplied by exponential delta G star by RT. This is in a nutshell, but we have to have the diffusivity term also to be added there. Okay, let us not go into that at this moment, but basically the delta G star, which is the activation barrier for the nucleation, controls the nucleation rate, and if the smaller the activation barrier, the larger the nucleation rate. So, that means if you can have a high cooling rate, one can have a small nuclei, large number of them, and that again controls the grain size. That is one of the technique by which people use, for example, rapid solidification processing, which we are going to discuss a little later, is one of those techniques which has been used by people to refine the grain size. Even we know from our typical foundry techniques itself that when you go from a sand casting to a metallic mold, from there to a copper cooled water cooled copper mold, so you can have higher and higher cooling rates and finer grain size. Okay. So, this is known to every metallurgist, and we also have another technique which has become very popular from almost last 4 decades or so, which is called inoculation. Okay. That means you take the liquid metal, add some kind of nucleating sites into it, which is what we call usually heterogeneous nucleation. So, if you can add a heterogeneous nucleating site, and if the site has some kind of a compatibility with the liquid metal with the solid that is going to nucleate, you can have a large number of nuclei coming out depending on the number of nucleating sites that you have. So, whatever is the number of active nucleating sites that you have in the liquid metal, that is going to decide ultimately what is the grain size that you are going to get. So, if you have a numerous number of fine nucleating sites available, if they are all active, then you have large number of these grains forming, and ultimately the grain size will be finer.
But only increasing the nucleation sites won't do, because you have to control the growth size, you have to reduce the growth.
That is true. So, that you can control it if you can somehow control the, if the whole liquid is having a large number of these nucleating sites. Okay. So, what happens is the grain gets nucleated on that, and as it tries to grow, the other grain which is nucleated on the other grain acts as an hindrance. So, you have a physical barrier for the growth of these grains. So, as a result, ultimately you see the two grains come and meet each other, and finally you get fine grain structure. Okay. So, one way is to have a large number of such nucleating sites, which we ourselves have done it in our department, and we have seen, we have developed a number of these grain refiners, which are called and these grain refiners basically depend on the type of metal, because it depends on the type of metal, what is the type of nucleating site that we can use for a particular metal. For example, if it is aluminum, aluminum structure is FCC. Okay, so you need to have a nucleating site which has some kind of compatibility with the FCC structure. That means the surface on which the nucleation is taking place, okay, should be compatible with the structure. So that means some atomic planes in the FCC structure should be having similar atomic arrangement, okay, with the surface of with the atomic plane which is parallel to the surface of this nucleating site, so that you can have a nucleation possible there. Okay, this is similar to epitaxy we talk about when we are talking of thin film deposition. Okay, but the problem is with all these techniques that we have talked so far, which are techniques for grain refinement, you can never achieve grain sizes below about 10 microns or so. Okay, 10 microns, maybe 5 microns. But if you really want to go into a few nanometer range, okay, you need to really go into newer techniques. Okay, and these techniques are basically either gas condensation, we will come to them a little later, and also there are techniques, for example, high energy ball milling techniques are available, or precipitation from the liquid state we can do it, okay, and also solidification at very high cooling rates, not as we usually observe during our foundry techniques, but at rates which are much higher, like what we usually see in rapid solidification processing, such as melt spinning and so on. So such techniques can lead to these nanomaterials, but the basic starting point for this could be, how do we define this nanomaterial? Okay, as everybody talks about, everybody says, can we say even a 10 micron material, call it as 10,000 nanometers and call it as a nanomaterial, just because we are telling the dimension in the time in terms of nanometers, okay, or is there any limit, okay, below which we can call it as a nanomaterial? The usual limit people take it is about 100 nanometers. Okay, but this 100 nanometer is not a real sacrosanct number, basically because it all depends on the type of material. So in principle, the definition of where you would call it as a nanomaterial is that size below which some property significantly changes. Okay, if we talk in terms of a, let us say, optical property, there are some materials such as barium titanate, okay, which are usually opaque, but the moment you take them below a certain crystallite size, they become transparent. Their complete optical property changes from opaqueness to transparency. Okay, and similarly there are some materials whose magnetic properties change, and in case of metallic materials we also know that their strength changes significantly in some of these nanomaterials. We also come into a regime which we will talk a little later, where the size is so small that probably it will not lead to any increase in the strength, which is, we call it the reversal of the Hall patch. Okay, we will talk about it a little later, where the grain size is so small that the Hall patch relation really cannot be used there, and then you can have what is called a softening effect there. So we will also talk it. There are some cases where people have proved it, but it is not still proved as a universal phenomenon. So still we can say there is a debate going on whether really a softening occurs, or is it system dependent, and probably in some systems it happens and some systems it does not happen. This is something has to be proved in future. But basically if you look at this picture, what you see is that any material is made up of the grain and grain boundary. Okay. So, and if you take a material which is basically made up of polycrystalline materials, of course, I am not talking of single crystals. So, if I am talking of polycrystalline materials, you have obviously grains and grain boundaries, and usually in most of the polycrystalline materials which we commonly come across, the grain boundary is very thin, and the volume fraction of the grain boundary in terms of the total volume of the material is very small, of the order of around 1% or so. Usually, if you look at the volume fraction of the grain boundary, the volume fraction of the grain boundary almost raises kind of exponentially if you talk of volume fraction of grain boundary as a function of crystallite size, and below around 10 nanometers or so, the size almost reaches around 50, the volume fraction almost reaches about 50%. Okay. You see here we have plotted the grain boundary volume fraction, the triple lines volume fraction, quadrupole nodes volume fraction. All of them give you an idea that, for example, if you look at the grain boundary, it reaches almost about 50% when you reach below about 10 nanometers, around 5 nanometers or so. Okay. How do we calculate this? Simply assume that you have a grain in the form of as a square or a spherical particle, and then imagine a grain boundary thickness of the order of around, let us say, a delta, let us say the size of the grain as d. One can calculate what is the volume of this grain boundary by simply finding out the total volume minus the volume of the grain, and this is inversely proportional to the grain boundary volume fraction, grain boundary percentage. If you say, this becomes inversely proportional to, if you derive the whole expression, it becomes inversely proportional to the d, the grain size. If we use about 10 nanometers, you reach for a grain boundary thickness of the order of around 1 nanometer. Usually grain boundaries have a thickness of about 1 nanometer. Okay. In principle, one has to also consider that as you decrease the grain size, the grain boundary thickness itself keeps on changing, and it keeps on increasing when you decrease the grain size below around 10 nanometers or so. Beyond about 50 nanometers, the grain boundary thickness does not change that much, but if you go to really very small grain sizes, the grain boundary thickness also will be larger, and as a result this delta is not a fixed number, but for all practical applications usually people assume the delta to be around 1 nanometer. And if you take that with this kind of a rough formula of grain boundary percentage volume fraction is about 3 delta by d, it will give you an idea that about 30% you get when you have about 10 nanometers, okay, 33% or so, and if you come to around 5 nanometers, you will see that almost you get about how much? If you come to about 5 nanometers, what would be the volume fraction from this? 60%. Okay. So you can imagine that you have now a material with about 50% of grain boundary. So the whole property of the material is going to be decided to a large extent by the grain boundary and not the grain itself. So far we used to think of the properties of the material basically depend on the grain structure and all the, for example, the Hall pitch relation, everything we talk in terms of the grain boundaries acting as the obstacles for the dislocation movement, and then so everything is dependent on the just the grain size without considering much about what is there in the boundary and how does this boundary affect the properties. And we usually know that the grain boundary is basically a disordered region when compared to the grain. As you can see here, the black regions are all the grains which are ordered arrangement of atoms, okay, and the grain boundaries which are basically the disordered region. In fact, long back when Gleiter has discovered these nanocrystals, okay, he even said these grain boundaries are gas-like structures. Though people have proved it a little later using high resolution microscopy that there is no such gas-like structure really in the grain boundaries, but definitely there is some kind of a disorder there. So because of that disorder, the properties of such a boundary is going to be different from that of the grain, and once the volume fraction of such region becomes very large, so one has to consider how the properties are going to be affected with such a boundary. And usually we take the property as just as a rule of mixtures. Okay. For example, if we know the property of the boundary, any property, for example, take it as x, If we know the property of the grain and the property of the boundary, one can take it as a rule of mixtures as the volume fraction of the boundary multiplied by the property of it plus the volume fraction of the grain multiplied by the property. But before that, one need to have an idea of what is the property of the boundary. Okay. So for that, one need to do, how do you think one can get an idea of what is the property of such a boundary? Is there any way? How do you know the property of a, let us say, a grain? If you want to know individually these two properties, any mechanical property, for example, metallography gives you the properties. Metallography gives you only the structure.
Suppose, for example, hardness I have to take.
Correct.
I will take hardness of the place.
Correct. So with the new techniques that are available, such as nano indentation techniques, okay, one can get an idea of the boundary properties without much problem. And one has now sophisticated techniques to visualize these boundaries. We have high resolution electron microscopy available to see the grain boundaries. We have also atom probe field ion microscopy available to see how the atoms are arranged in such a grain boundary. So such sophisticated techniques are available to see the structure and also get to know what is the atomic distribution, what is the composition of such a grain boundary, okay, using techniques such as atom probe field ion microscopy, APFIM people call it, or 3-dimensional atom probe, 3D APA people usually refer to as, and such techniques can be used to find out the composition and structure. Structure can be obtained from high resolution electron microscopy, as I mentioned, and one can get the properties using techniques such as nano indentation. Okay. So these are some of the techniques which can give you an idea of the properties. And before we go into the properties, we need to understand what are the various types of such nanomaterials that are available. Usually we broadly divide them as 3 types. Okay. In fact, I should say even the 4th type, because the clusters are usually called as 0-dimensional nanocrystals. Okay. If you take a few atom cluster, okay, which can be formed because of the evaporated atoms coming together forming few clusters of few atoms, such clusters are usually referred to as the 0-dimensional nanocrystals. Okay. Then you can talk of 1-dimensional nanocrystals, such as if you have nanowires, okay, or nanotubes. People are talking about carbon nanotubes, so you are all aware of. Okay. So such nanotubes can be really called as 1-dimensional nanostructures, and one can have 2-dimensional layered structures. Okay. You can have multi-layers of nanocrystals, and one can also have 3-dimensional equiaxed nanograins. So these are the 4 basic classifications of nanomaterials, but now one can have further classifications depending on whether it is a single phase material or a multi-phase material. Okay. For example, as you can see here, that if the composition, chemical composition is the same, if you have 2-phase material, let us say, okay, you can still have layered structures with each layer having the same composition, but they are deposited as layered structure. Okay. So one can have layers of the same composition, one can have a rod shaped nanocrystals which are of the same composition, various rods brought together, or various wires of nanowires brought together, that is one possibility. And you can have the grains of nanocrystals, various grains, each one having the same composition brought together. One can also have different compositions, again similar possibility of a layered structure or a rod like structure or a equiaxed grain structure, where you can have different compositions. Each grain has a different composition. Okay. One can make various nanocrystals of various grains and various compositions, bring them together and compact them, and you will have a heterogeneous property. Okay? And depending on the application, one can think of such a thing. Okay? And similarly, you can have the grain boundary composition different from that of the grain. For example, if you have a layered structure, the composition of the interlayered region can be different. So, one can have such materials with the composition at the boundary being different from that of the composition in the interior, and similarly you can have nanocrystals of a composition dispersed in a matrix. For example, nanocomposites, which people talk about nowadays. You can have a matrix. In fact, that is what has made the definition of composite itself is very vague. Long back we used to define a composite as something which you physically introduce, okay, a reinforcement into a matrix. Okay, for example, starting from a concrete or even a bone for that matter. These are natural composites. For example, wood and bone are natural composites, and we have the first man-made kind of composite probably is a kind of a concrete. Okay, so we are all aware of concrete, which we see in day-to-day life, but at the same time these are all real macro composites. Okay, but we have come from that a long way into the nano composites now, where you can have a very fine particles of the nanomaterial regime deposited or dispersed into a matrix. Even the matrix can be a nanomaterial, so you can have such a region that materials having nano size with different properties can be brought together and compacted, and you can have a composite. Okay, it is not only that you have a matrix with particles, or you can have grains, nano grains of two different materials can be brought together, and you can have a composite that way. So, the definition of a composite itself has to be looked in carefully, that any material with more than one phase, in principle people have started calling them as a composite. If that is the case, even a steel for that matter should be called as a composite. Okay. So, because you have more than two phase, more than a single phase there, and such a material can be called as a composite. So, what is important is that you have two phases, each one has a different composition, or different structure, basically different properties, and bring them together so that you get a property which is better than both of them. Okay. So, that is what is going to be a composite. And how do we make them? We can make them by various techniques, basically from three sources. One is you can have it from a vapor source, second you can have it from a liquid source, third you can have it from a solid source. So, if we take nanocrystals, can be synthesized basically from a vapor or a liquid or a solid. When you talk of a vapor, basically when you take a liquid and evaporate it, what you get is either atoms in the vapor form, okay, or molecules which are dispersed in the space. And if you can bring them together by a condensation technique, you can get those clusters. You can see the single atoms can be condensed to form clusters, and those clusters, if you compact them, you can get nanomaterial, three-dimensional nanomaterial. Okay. So, that is one technique, which is what we call cluster assembly. Okay. And such a technique is what is the IGC technique, which I have told you, inert gas condensation technique, which is regularly used by many physicists particularly, but the only restriction of such a technique is you cannot produce all kinds of materials. First of all, you should be able to evaporate something, okay, and then form in the form of vapors, particularly high melting metals. Okay, it's very difficult to make such nanomaterials using such a technique. And what also is important is, first of all, before you evaporate, you have to evacuate the whole chamber, isn't it? So, for evacuation of the whole chamber, so if you want to produce large quantities of materials, you need to have a large chambers, and these large chambers have to be evacuated. So, as a result, so there are limitations in terms of the capital investment that is required for such a technique, and the total quantities of materials that you can produce by such techniques are not really large. Okay. So, in India at the moment there is only one place where you have such a IGC technique, that is in University of Madras, okay, in the nuclear physics division, one Professor S. Ramaswamy. Okay. He has been working on this, and he has developed a IGC instrument, okay, fabricated it here itself, and he has been making a number of pure metals, okay, and also some oxides. This is another advantage, that that you can evaporate a metal and have some kind of an oxygen atmosphere, okay, so that the metal vapors react with the oxygen, and you can have a nanoparticles of oxides deposited, okay, and any other, maybe you can have a nanoparticles of nitrates deposited, okay. So, by controlling the atmosphere, so one can have such reactive synthesis possible in the vapor stage, where the gases atmosphere reacts with the nanoparticles, okay. So, this is basically a vapor condensation technique, and once they are condensed onto, basically you have a chamber with a cold finger, which is basically nothing but a tube with a liquid nitrogen which is circulated through this tube, and the tube is rotating, okay, and you have a kind of a scraper which scrapes off all those nanoparticles as the tube rotates. So, as the vapors get condensed onto the tube, which is at a much lower temperature, and the scraper scrapes off all those nanoparticles which drop into a collection chamber, and you can have a compaction facility, so that before exposing these nanoparticles to atmosphere, you can even compact it there itself. Okay. So, there are facilities such as compaction within that chamber itself, so that everything can be compacted either in argon atmosphere or in vacuum, so that the particles are not exposed, because you know that nanoparticles have a very large surface area to volume ratio, and because of which, once they are exposed, they may even become pyrophoric, okay, that they may even burn, or they may get oxidized, and their properties might change. So, as a result, one has to take special care in handling these nanomaterials. Okay. Another possibility is that you can have these nanoparticles which are formed dispersed in some kind of a fluid. Okay. Have you heard of ferrofluids? Okay. So, magnetic ferrofluids, okay, where the magnetic particles are dispersed in a fluid, okay, which is some kind of a surface active agent, so that it does not bring in the nanoparticles together for agglomeration. It prevents the particles from agglomerating, so that these nanoparticles are uniformly distributed in a liquid suspension, and these ferrofluids are being used nowadays for the bubble memory, for enhancing the memory in the computers. Okay. So, there is a lot of work going on such ferrofluids. Okay. So, the whole liquid behaves like a magnetic material now, okay, because you have so many nanoparticles of these magnetic nanoparticles dispersed in a liquid like that. So, this can be done by such a technique. Second route is from the liquid. When we say from the liquid, there are two possibilities again. One is you can take a liquid of a particular alloy, rapidly solidify it, so that you provide a large undercooling, so that you get a very fine grain structure. There are a number of alloys where people have been able to make nanocrystals by such a technique. Okay. Or the other possibility is that rapidly solidify a liquid to get a glass, and then heat this glass, because we know that glass is always metastable material, okay, metastable structure. So, you can reheat this glass in a controlled fashion, so that some nanoparticles can precipitate out of this glass, because crystallization of the glass. Okay. So, if you can cool the liquid rapidly, such that the cooling rate is higher than the critical cooling rate that is necessary for preventing any crystallization during solidification. So, you can get a glass as long as you come below the Tg. Okay. Once you come below the Tg, you have a glass. Take this glass, heat it again, so that you can have a uniform distribution of fine nanoparticles. Okay. That is another technique. Okay. But these are all basically used for mostly for metallic systems. Okay. But there are also other systems, whereas for example, you want some oxide nanoparticles from a liquid route. There are a number of deposition techniques that are available. Okay. For example, sol gel techniques. Okay. So, solution gelation people call it. Okay. So, where you have basically a liquid and you bring the conditions to such a state that some precipitation occurs, either by heating or by adding some other reagent which can break this solution to give out the ions, and which get agglomerated and form nanoparticles and get precipitated out. This is simply just precipitation from liquids. Okay. There are many such precipitation techniques available. Most of the chemists use such precipitation techniques to produce nanomaterials. Here one advantage is you can really do on a large quantities. If you want, you can take few kgs or even tons, probably one can think of. Only thing is one has to control the conditions. But the only limitation of this is most of the chemical reagents people use are really toxic. So, because of which, so you have a problem of environmental pollution. So, how to take care of these effluents that come out of it, okay, the byproducts that come out of it, but hopefully people will come out of some solutions for that. So, you have such chemical precipitation techniques or electrodeposition techniques. Okay. We know electrodeposition we use for plating. So, same electrodeposition technique can be used by controlling the current conditions and the voltage conditions and the concentration of the medium, such that, and the temperature of course, okay, such that you can have nanoparticles deposited on a substrate, particularly when you want to have high wear resistant surfaces on any substrate. You can have such electrodeposition techniques. You can also talk of lasers, okay, where again you take a bulk material, melt only the surface layer, and the cooling rates being so high that you achieve rapid solidification conditions, and finally nanoparticles are deposited on that. And when you melt it also, you can introduce some other material, for example laser surface modification or laser surface alloying people talk about. Okay. So, once you melt the top layer, then introduce some other material. For example, simply if you are melting a titanium, okay, by laser in a atmosphere containing nitrogen, immediately this liquid titanium which forms can react with the nitrogen which is there in the atmosphere and can form a titanium nitride coating, thin coating of titanium nitride. Probably if the conditions are fine enough, you may have them in the nanocrystalline form. Okay. So, that you can have a hard nanocrystalline layer on the surface of otherwise a ductile material or otherwise a soft material. So, one can have a soft bulk material with a hard coating of nanomaterials on it. Okay. That is from the liquids. So, these are all the techniques from the liquids. Then the third possibility is from the solids. How do we do from the solids? Break down a macro material into a nanomaterial. So, take a macro material, okay, such as powders, let us say atomized powders of the order of around 100 microns or about 300 200 microns particles, and such particles, take them, put them in a ball mill, okay, or any other technique, okay, where you can really break the particles into finer and finer size. This is similar to just comminution which we do, okay, in a mineral processing. Only thing is there the energy levels are so small to really take these particles to the nano size, but there are a number of high energy milling techniques available where one can really make nanoparticles out of it. Okay. The only difference between this technique and the vapor deposition is here it is what is called a top down approach. Top down approach means you are starting from a macro material and going to a nanomaterial. Okay. In a vapor deposition, it is like a bottom up approach. You are starting from atoms and then building the atoms together and then forming a nanocrystal. Okay. So, both are two different routes, okay, and liquid is somewhere, it falls somewhere in between. Basically, liquid is a homogeneous mass, which on cooling you are developing, either on cooling or on deposition you are developing nanocrystals. And both these routes, depending on the route, people have found that the properties could be slightly different. The same nanocrystalline size, if you make it from a gas condensation technique or by a ball milling, okay, the properties could be slightly different. Why do you expect the properties to be different? Sizes are the same. I have made a nanocrystal of about 10 nanometers or 20 nanometers of a pure iron, let us say, made by ball milling, and the same pure iron made by gas condensation, compacted both of them, study the mechanical property, and I find that there could be some differences.
Sir, internal energy would be different.
The defects inside the material would be different, and because of the grain boundary structure could be slightly different. Okay. So definitely just the size itself is not the answer. Okay. So size controls the properties to a large extent, but the grain boundary structure also has a lot of role to play. So one has to consider that also into picture. Okay, we'll stop now. We'll stop.